Okay, so I think my screen is visible. So we were solving tree problems. So today we will start with. I think we should start with this medium problem. Okay, lowest common ancestor. Given a binary tree, BST, binary search tree. Okay, find the lowest common ancestor of the ancestor LCA of two nodes, two given nodes in BST. According to definition, the lowest common ancestor is defined as the between two nodes P and Q as the lowest node T that has both P and Q as descendants, where we allow a node to be descendant of itself. Okay. So basically, this is a binary search tree. So in binary search tree, each node can have zero or at most two children, and the node's right children node is always greater than the root node, and left node is always greater than smaller than the root node. So basically, that is a binary search tree. So basically, in order to find the ancestor, we are given two children's, uh, 2 and 8. For example, this is 2 and this is 8. So we will be finding their first parent. So in this case, 6 is their first parent. Okay. So here we have two children, 2 and 4. So their first common parent is 2. As the question says, a node can also be descendant of itself. So we will consider 2 as descendant of itself. So 2 and 4. Okay. So basically, we need to find a parent of two nodes. Okay, so one way I'm thinking is suppose we here we need to find parent of two. So we find a path till two. So path till two will be 6 and 2, and path till 8 will be 6 and 8. So the first common element in their path is 6. Okay. Suppose instead of 8 I was given 9 here. So for 9 the path would have become this one. So here this 6 will remain same, means they have a common ancestor at 6. Means we need to have two lists which will store a path of both children's, and then in that path we will find first common element from the right, and that element will be our lowest common ancestor. Okay, so in worst case, that would take a big of n time and big of n time complexity in the case of a skewed tree. So basically, in the case of a skewed tree, a tree n nodes where height of that tree equals to n. So that is the definition of split tree. Okay. So as our tree is binary search tree, so we can search for a element easily. Suppose we are at a root, and if we suppose need to find 3, so we will check if our current element 3 is smaller than 6 or it's greater than. If our current number is smaller, then we will move to left. So here we will move to left. Okay, so now we will compare 3 with the 2. So 3 is greater, so we will move to the right. So now 3 is smaller than 4, so we will move to the left. So that's how we will search for an element in a BST. So that is why we can use path find. We can find the path. So we need a list. Actually, we need two lists. First list, let's call it let's list of integer. Okay, so path to P, that will be path to P node. Okay, and we will okay, we will also define, that would be a new list. We will also define path to Q. Let's make this capital, path to Q. That would also be a list. Okay, so first we will find path to P node. So let's define a temporary node, temporary tree node to iterate the tree. Okay, so while my so I think it is guaranteed that P and Q are present in the P is not equal to Q, and P and Q will exist in the binary search tree. So we don't need to bother about whether this will exist or not. So what temporary variable? Okay, so while our temporary variable is not equal to null, let's say, what we will do, we will add that node's value into our path. And if our temporary node's value is greater than the P value, let's see one more thing. Okay, so our own node values are unique, so we don't have a case where our value will be equal. So if my value is greater, if my current node's value is greater and my P is smaller, so in that case I need to move to the left part. Okay, otherwise I will move my temp to the right part. So that's how I will find part to my uh, wait a second, let's return null here. So this will give my path to the P node. So for this example, P is 2. So path to P node will be 6 and 2. So let's see if we are getting correct output. Printed. And so we will print our list path to P. Wait a second, we are getting some error. So we need to write here array list. Okay, so my path to P is only two. Okay, so I haven't added root node, I guess. No, no, no. Wait a second. So this is my okay. So I can do one thing is if my temp dot value becomes equal to if I have found my children node, then in that case I can return my loop, break my loop. So yeah. So we are getting 6 and 2. So that will be part to my second node 6 and 2. Okay. So suppose my node is p dot value. Okay. Let's say I change my I want part till 3. So for now let's change value of p node p dot value is equal to 3. So let's see what path to 3 will look like. Okay, we are getting 6 3 directly. I think our path is not getting modified. Okay, so this is a path function p dot value. I think we can't modify the input, so let's see. So this is my path to p. So similarly, I can calculate path till uh, q. So instead of rewriting the function, we can define a generalized function that will look like that will return our integer list find path that will take a temporary node as input and also the node till which we will find our path. So let's we can also call target or mm, let's say code it target node. We can define a array list and okay in this array list we can paste over this function. Okay, so this will be part to p and instead of p we will generalize it for our target node. So we will replace p. Okay, and at the last we will return our path and this will be equal to path to p will be equal to we will call our find path function and pass temporary node and our target will be initially will be p. Okay, so after we have found our target we will reinitialize temp to root and we will find our path to q and path to q will be find path temporary variable and we will pass q. Okay, so now these arrays will store part to p and part to q. So let's println part to p and path to Q. Okay, we can't define a function outside of a class, so we need to define it inside. Okay, so now my path, let's move this part here and description part here. So for first case, my path to P node, which is 2, is 6 and 2. 6 and 2. And for 8, it is 6 and 8. For second example, my P is 2 and my Q is 4. So let's see my path. So my path is 6, 2 for the 2 node, and for 4 node it is 6, 2 and 4. Okay, so in order to find lowest common ancestor, we will find this first common element. So here the first common element is 2. So answer will be 2. And as of previous example, the first common element is 6. So answer will be 6. And for the third example, we have a 2 node and under it we have a 1 node. So for this answer will be 2. I think so. 2 is common element. So what we can do is we need to find a first common element from last in both paths. So that will be our answer. Actually, we need to return the tree node itself. So instead of putting the value, we can store tree node itself. Here we can return tree node, and instead of storing the value, we can store the node itself. Okay. So I think to find the first common element, we can use a set. Let's say we use a set here and we add 2 and 4 to our set, and then we start from the last. We check if our set contains 4. No, it doesn't contain. We will check if our set contains 2. Yes, our set contains 2. So then we can return 2. Or I think do we have another better approach? Tree. No. Okay, so let's use set. So let's initialize our set of integer, as our values are unique, so we can use a set. So as set, in our set we will add for tree node in path to P. So we will iterate this path and we will store that node's value into the set. Okay, so we have added this paths all node into our set. Now we will iterate this path path of q from last. So for int I equals to, we will start from last index, which will be uh, size minus 1, and we go till last. And if our set will contain to q dot get ith node dot value, if our set will contain that value, then we have found a, so what we have done, we have added these values to set. Now we are iterating this list from last. We will check if this value exists in our set. No, it doesn't exist. If it, we will check if 2 exists in our set. Yes, it exists. So we will return. So this means the value exists in our set. So what we will return? We will return path to q dot get ith node. So this will be a node because we have a list of node. So let's try running it. So basically this code, what this code will do, path to p node, then this will find path to q node, then this will find first common node in path. Okay, so our test cases are running perfect. So I think we can look for some edge cases. Suppose let's see if our root can be null or not. Okay, so number of nodes in our root is 2. So we must have p and q. So as said in the constraints, that p and q will exist in binary search tree. So I think our approach will work perfectly. Okay, so we have a summation. So I think we should analyze time complexity. So suppose my tree have n nodes. So in that case, the path algorithm can take a big of n time, which is where n means number of nodes in my tree, and similarly this will also take big of n time, and or adding the path in the set will also take big of n time, and finding the last element will also take big of n time. So our overall time complexity is big of n, as we are not using any nested loops. So big of n will be our time complexity. So can we think of a better way in which we can solve this problem? I think we can use a recursion. We can use recursion. So how we can use recursion? What we can do is we can maintain variables like if we have found two, means two booleans, one indicating whether we have found two or whether we have found eight. So whenever we have found a variable, we can mark it as true. Okay. Hmm. Let's remove this code and see if we can. So let's not waste time. Hmm. So find LCA. Let's define a function where we have root node, p node, q node, and we will maintain two booleans. Find LCA. We will define a tree node. Okay. For now, let's take this function returns a void, nothing. This function returns nothing. So if my root becomes null, so I will simply return. Now I will move to the left part. Find LCA, LCA, root dot left, P Q P found, Q found. One call will move to right. root dot write p q q found. Okay, given a binary search tree, find the lowest common ancestor of the two nodes in BST according to definition. The lowest defined between the two nodes as the lowest node, both Q and descendants. Okay. Suppose if my root dot value is equals to p dot value. So in that case, my p found will become true, and if my root dot value becomes equal to q dot value, then q found becomes true. Okay. Let's see if this works. Mm, it is not working. Okay, let's say I run my function for this part. It will go full fledged to the left. Then it comes here. Suppose this becomes true. Let's ask GPT. Okay, we have a answer as null. So we are putting these variables. I think GPT can help us. What's wrong with my solution for finding LCA in BST? Your solution has several issues that prevent it from correctly finding LCA. Issues, these are local variables. Okay. Any changes to in one recursive call will not propagate to other calls. As a result, the logic that takes it both will not work as intended. Okay, so am I supposed to do this in this way? That boolean p found is equals to false, q found equals to false. Okay, so the question is saying we can use property of binary search tree to find the longest common ancestor. If both P and Q are smaller than the current node, that means LCA exists in left subtree. If both P and Q are greater than it exists right subtree exists, the current node is the LCA. I am not leveraging the BST property. Okay, so let's ignore GPT for once and try to set these as global variables. So then will our solution will become a generalized solution. Let's say, okay, so we are getting 8 as the output because at 8 we are getting both as true. We will ask our GPT to correct this code. Ask GPT to provide correct solution. Make corrections in this code itself. I think what we can do here is when we reach it, here our flags, both flags are getting true. So what we can do here is what we can check that enhancing accuracy, tracking progress, tweaking the strategy. I think GPT is also taking a lot of time. Refining tracking, focusing on efficient tracking. It's not modifying my approach. Or it has modified. Let's see if this works. Okay, so Okay, left count, right count will return. Okay, so the main approach which should be used for this question is like uh, if my p dot value is smaller than root and q dot value is also smaller than root, then in that case I will return. I will move to left side p and q. If my both values are greater, then that means I need to move to the right. If none of these conditions satisfied, so my current root will be the answer. I think that was the approach GPT was giving us, which is this approach. Okay, so one condition I can also have in my root is null. This condition will we will never reach this condition because we do the p and q node will always exist in our list. Okay, this works. So we have binary tree, level order, transversal binary tree, right side view. I think these questions are pretty easy. Should we waste our time on these questions? I think these two questions are pretty basic. Let's pair 2 minutes for these questions also. We can solve it in 5 minutes. Count good nodes in binary tree. Okay. These are the good questions, I think. Okay, so these are the good questions. So what we will do now is we will do these two questions first. This one and this one. Wait a second, guys. I'm creating some message. Okay, let's quickly do these two problems. So now we are doing, where's the tree? These two problems, level order transversal and right view of a binary tree. So why I am picking these two problems uh, simultaneously? Because these problems are similar. Means, so in order to, so first, what does a level order transversal mean? So level order transversal means this is a first level. So we will print 3. Then second level 9 and 20. Then third level 15 and 7. So you can see first level is 3. Okay. Second level is 9 and 20. So basically we need to print the levels of the binary tree. So order transversal will be solved using breadth first search BFS. So in order to implement BFS, we use a priority queue. So how we'll gonna use a priority queue? Let's see. So we will initialize a priority queue. Okay, so our answer is in this format. So let's first define the answer format. So this will be our answer and list of list, and at the last we will be returning this answer. So we were initializing a priority queue. So priority queue priority queue of what we need to return integer. So we need priority queue of tree node. Okay, pq new priority queue. Do we need a priority queue? I think we can only need a queue. We need only a queue. Okay, so in Java we implement queue using linked list. Okay, so first what we'll do, we will add our root to our queue. Queue dot add root. Okay, so we have added queue to the root, and while our queue is not null, queue is not empty, we will take out, we will find size of our queue. So initially the size of the queue will be 1 because we have added only root. So this is my first level. So what will I'll do here, I will initialize a list integer current level new array list. So at this moment, my list will contain the current level. So I will iterate I will pop all the element present in my list, in my queue. So current element, current node is list, tree node, current node is queue dot poll. We will add this current node's value to our current level. So dot add current dot value. Okay, so we have added its value. Now suppose we have popped out 3. So now we need next level. So next level will be the left node of the 3 and right node of the 3. So we will check if left node of the 3 is not null. If it's not null, then we can simply add it to the queue. Means what we are doing is we have added first level to the queue, then we will remove that first level and fill the queue with the second level. So now we will add the second level element, which is current dot left. Similarly, we will use the current dot right part. And at last, what we'll do, we will add our current level to our answer. Answer dot add current level. And at the end, we are returning our current level. So that is how BFS works. So let's try running it. Okay, we are getting a error saying we are accessing null. Okay, so I think we haven't handled this case where my root can be null. So if my uh, let's handle it here. So if my root becomes null, in that case I will return my answer as it is. So I have nothing. I don't have any levels in my tree. Okay, so let's submit it. I think I submitted it multiple times. Submissions. Okay, so I submitted it many times. So let's copy this solution. Okay, so my next question is binary tree right side view. So what does right side view? So we have just found the level order transversal. So in level order transversal, the last element in every level will be my part of right side view of the binary tree. So how I can find? So I was adding every element. So now my answer will be in this form. It will be a list of integer, and I don't need a current level part. So basically, this is a template for a level order transversal. So now what will I do here? I will check if my uh, I is equal to size minus 1, means if it is a last element of the my queue, in that case I will add it to the answer dot add. Uh, let's see current element uh, tree node current will be q dot poll, and if my I is equal to size minus 1, in that case I will add its value to my answer, and at the end I will return my answer. So I think this is a right side view for binary tree. Okay, so let's submit it. Okay, it was also pretty easy. That's why I was saying it's a 4 to 5 minute work. So let's move to the next question. So the question says, given a binary tree root on node X in the tree is named good if in the path from root to X there are no nodes with value greater than X. Return the good nodes in the binary tree. I didn't get the question. So what does question saying? Given a binary tree root, okay, a node X in the tree is named good if in the path from root to X there are no nodes with value greater than X. Okay. So nodes in blue are good. Okay. So 3 to 3, path of 3 to 3 doesn't have any greater node. 3 to 4 also doesn't have node greater than 4. 3 to 5 doesn't have node greater than 5. 3 to 1 have a greater node 3. 3 to 3 doesn't have any greater node. Okay. In, okay. So we need all the paths. Means we need all the nodes. This is a good question. Sounds like a good question. So number of nodes are in the range 10 raised to the power values between this variable. Let's think. Okay, I have a tree. And I need to find good nodes. Given a binary tree root, a node x in the tree is named good if the path from root to x there no node should be greater than x. Okay. Suppose I start with 3. Now my max is 3. Okay. So I will check if this my current node is greater than. Okay. Then I'll make my max as this. My max will be still 1, 3. Okay. So I think I should maintain a max variable which will indicate the max value in the path till now. So initially, suppose my max variable is minus something like minus 10 raised to the power 4 plus 1, 4 minus 1. So I compare 3 with the minimum value, no, maximum value. So 3 is not greater. So I will have a good node. Now I move to this path. Now my max is 3. So I will check if this value is greater than max. No, it's not greater. So this will be not path of my good path, not part of good path. Now I move to this. So I will check if this value is greater than or equal to. Yes, it's greater than or equal to. So okay. Now I move to left part. Okay. Yeah. So that will work. I think that will work. And at the end, what I need to return? I need to return number of good nodes. Okay. So that will not be issue, I think. So value left node, right node. So find good nodes. I'm initializing a function find good nodes, giving a root variable and integer dot minimum value. Okay. Public void find good nodes tree node root int max value. Okay. If my root is null, then why I'm forgetting to put a equal, I will return. Else I will check if my root value is greater than my max value. In that case, I will increment my answer and I move to the left part. And in left part, what I'll gonna do is I'll gonna pass math.maximum of these values. Similarly, as I will move to the left part. and here I will move to the right part. Okay, so I need to increment answer. So let's define a global variable, int answer, which is 0 initially. At the end I will return that answer, and here I will increment that answer, so answer plus plus. I think this approach should work here. Okay. Mhm. It's not working, guys. I think it should be greater than equal to. Okay, it's working. Let's try submitting this. Okay, we have a acceptance. I think my previous solution is also pretty similar. Let's see. I think we can solve this problem iteratively also. We will try to solve it iteratively also. So let's first see my previous solutions. Okay, so previous solution was in September 22. I think this is the similar approach. Count variable max as the max is equals to root dot value and passing the max. Pretty basic. So to do a improvement from the past, we should implement is it iteratively. So to iteratively transverse a tree, we need a stack of tree node. Let's call it stack new stack. Okay, so initially what we will do is initially we need to move to the right, to the left of the stack. Okay, so we were solving this problem using stack. So initially we will moving to the right part. So uh, while my root is not null and or my stack is not empty. Okay, I need a path from my root node to a given node. So how I can figure out the path? I think I can't using stack. Can I? I can transfer, but I can't store like path. Okay, so let's first transfers. If root is not equal to null, if root is not equal to null, what I will do, I will put that root to my stack. Okay, and move my root to root dot left part. In else case, my stack will not be empty. Means my root is null, so basically I have nothing to iterate. For let's take this example. So initially I am here, so my root is not null, so I have added this to stack and moved to left part. And again my root is not null and stack is also not null, so I have moved to this part, added this part and moved to this part. So now my stack have 3 1 3, and what I will do now is I will move to the left part. So now this part becomes null. So now I will go into my stack and pop out my element. So let's say, should I pop out? Yes, I should. Hmm, tree node current equals to stack.pop, and I can move to the move my let's take a temp variable instead of root. So command tt, okay. So temp variable, and if my temp becomes temp should be temp dot write. Okay, so I will pop out this element and move temp to the right. So now my temp is again null. Now I move right to this part, then again null, move to this part. This is 4. Now my temp is not null, so I will add 1. Mm, if okay, temp is not null, 1, and again I will move to the left part. Now it becomes null. Then I'll pop 1, and I'll move to my 4. So this is how I'm doing it. Iteration 1. Hello.
हेलो नरेश। मैंने जो तुम्हें सीआरएस किया हुआ था ना,
Okay, so given a binary root x in tree is named path. So if we are at a node 4, okay, so I think we can also maintain a maximum variable in our stack too. Let's just print system dot out dot print temp dot value. We need to return something, so let's return 0 for now. Let's see what we are getting. We are getting some exception. Temp is not null. Okay, temp should be current dot write. So let's move this part to here. Let's see over. Okay, so we are getting printed 3, then 1, then 3, then the right part 4, then 1, then 5. So this is the order in which we are getting printed values. So I think we should also put a max value with the stack part, so we will have a track of the maximum value. Okay, so we need a pair, so let's define a pair. So public class pair. Let's make this class private. We don't want other classes to access it. So pair. Okay, so pair will have a tree node. Let's call this node and max value max. So let's initialize these values. Okay, so this node as node, this dot max value as max value. So now we have a pair. We will have a stack of the pair class. So okay, how we gonna track the previous value? So till 3, till 3 we don't have any maximum value. So over 3 will be maximum. Then we reach 1. Stack dot peak will be parent. Okay, in 3's case, stack peak will be parent. Then we reach this value. We pop this value. There's nothing in. Then we pop this value. Then we pop this value. So we have popped this value. So here 3 1, this case 3 3 4, then to the right 2. Moving to right. Okay, if stack is empty, what modification we can do here? Temp null. Uh, temp dot value is greater than or equal to stack dot peak dot this node dot its value. Suppose we have answer variable. Okay. new pair, temp, and max value. Okay, so initially the max value is 3, but our stack is empty, so we will not go into this part. Then move to we will add a max value, which is 3, and then we move to this part, and we check if our this value is greater than the 3. No, it's not greater, so we will not update our part, this part. Then we move to this part and check if our value is greater than stack dot peak dot max value. Max value, maximum of these values. Okay, so we have reached our end. Then we will pop the pair and move to the right part. We have nothing on the right part. Then we again pop. We have nothing on the right part. Then we again pop. We have 4 on the right part. So temp is not null. We have popped our current pair and we move to the right. Okay, so now our stack is empty. So we need this maximum value. Maximum of these values. Hello.
हेलो नरेश।
हाँ ऋषु।
5-10 मिनट बाद ना एक बार देख लेना यार, कल के लिए ये मैं रीशेड्यूल करवाया हूँ, ठीक है? 5-10 मिनट बाद एक बार खोल के सिस्टम देख के कंफर्म करना है, ठीक है दोस्त?
क्या चीज की ये हो गए?
रीशेड्यूल हो गया, राइट? मेरे को पिंग कर देना बस, चलेगा दोस्त।
तो ये तो वो एक बार मेल करेंगे कंफर्मेशन, उसके बाद देखना है।
हाँ, उसके बाद मैं होल्ड पे रखा हूँ उसको, ठीक है दोस्त? चलेगा।
ठीक है, मैं देख के बता दूंगा आपको।
थैंक्स यार।
ओके ऋषु। We need maximum part from the think this will work. Wait a second. What does it even mean? Perfect. Perfect. We have an iterative solution for this problem. Looks pretty good. Let's ask GPT-2. Can this be better? Why I am using O1? Should have used 40. We have limited queries of O1. Yes, you can make it cleaner, more robust, ensuring each path maximum values stack itself rather than relying on single variable max. We'll see. So GPT have provided us a better solution. Let's look at our GPT solution. So stack pushed root and root's value into the stack. While stack is not empty, it popped the current pair, current node, max so far. Okay, max so far. If a node dot value is greater than max so far, update max so far. Okay, updated max so far. Push children with the updated max so far. Max node dot write is not equal to null. Okay, it's pretty simple approach. Okay, okay. So I think we are good to sleep now. I think it will take another 2 days to solve trees. Okay. Thank you for watching, guys. Good night.